All right, this will be the key for the most recent homework, fundamental theorem of algebra. We'll get started. State the number of complex zeros for each function. Remember, underneath complex is basically all number types. So if we include all number types, then we can apply the fundamental theorem of algebra, which states that the degree is the same as the number of roots. So this is degree 3. So complex roots or complex zeros equals 3. No more, no less. This one would be a 5. For this next part, the imaginary zeros, we have to remember that these come in pairs. So it's not possible to just have one. You can always just have 0 imaginary zeros, or you can have 2. We can't go up to 4 though, because then we're exceeding our total number, which is 3. This is pretty much the exact same problem. I meant to make those a little different, but forgot. Now real zeros, this is a little bit trickier because I know that the total between real and imaginary must be 4. That's our fundamental theorem of algebra. All right, so that's by the fundamental theorem of algebra, we know the total must be 4. So imaginaries have to come in pairs, so we can have either 0, 2, or 4. To balance this out, we got to make it so it adds up to 4, so this would have to have 2 real, or 4 real, 2 real, or 0 real, so that our totals are still 4. And so this is our answers here. We either have 4 real, 0 imaginary, 2 real, 2 imaginary, or 0 real, 4 imaginary. Over here, the total is 3. For imaginary, I can have either 0 or 2. I can't exceed that. And so for count, it either has to be 3 or 1 real. There's our possible number. All right. State the possible rational zeros. So these are of the form P over Q. So I just got to list down P equals 1 or 2. Q equals 1, 3, or 9. Now we make all the fractions possible with P over Q. So we can do 1 over 1. We can do 1 over 3. We can do 1 over 9. We can do 2 over 1, 2 over 3, 2 over 9. That's a duplicate because it's the same as 1/3. Let me rewrite this list, simplify it, and add a plus or minus to the front. 1, 1/3, 1/9, 2, 2/3. All right, and I'll skip the next one in favor of going on to number 9. Find all zeros. Just want to double check this is recording. Yeah, had some issues. Looks like we're good. Okay. Finding the zeros. Pretty much every one of these is a different factoring technique. Number 9 here, we want to factor by grouping. The greatest common factor is an x squared, leaving behind an x minus 13. 1, leaving behind an x minus 13. We regroup x squared minus 1, x minus 13. This one here gives us a 0 at 13. This one here, we should set it equal to 0 and solve. And we'll get x equals plus or minus 1. And there's all 3 of our zeros. 1, 2, 3. All right, here we can set this equal to 0. Subtract 125 from both sides. get x cubed equals negative 125. Cubed root. The cubed root, I'm pretty sure that's negative 5. Just want to be extra sure. It is indeed negative 5. X equals negative 5. Now to get the remaining two roots, because fundamental theorem of algebra states there should be 3 roots, what I'm going to do is a little bit of synthetic division. 1, 0, 0, 125. Put a negative 5 out here. Add, multiply, add, multiply, add, multiply, and I get this new quadratic. As a remainder 0, we knew it would. I get the quadratic x squared minus 5x plus 25. I want to put that into the quadratic formula. So let me do that now. I've got negative b plus or minus the square root of b squared minus 4ac, so I think that's 100, all over 2a. It's going to become 5 plus or minus the square root of negative 75 all over 2. I can rewrite that as 5 plus or minus square root of 25 times the square root of 3 is the square root of negative 1 all over 2, which then simplifies to 5 plus or minus 5 root 3i all over 2. So there are those 3 roots. One's right there, and x equals this second root right there. Okay, moving on. Number 11. This is quadratic form. You can set up a variable if you want, but hopefully you'll do enough of these that just simply jumping straight forward to this isn't too big a step. I know that if I set up my factors like this, when I FOIL it out, I'll get an x squared, or an x to the fourth, an x squared, and a constant term. Now I just need 2 numbers that multiply to be negative 7 and add to be negative 6. Those numbers are negative 7 and positive 1. And we solve these. X squared minus 7 equals 0. X squared plus 1 equals 0. X squared equals 7. X squared equals negative 1. Square root, square root, square root, square root. X equals plus or minus the square root of 7. And x equals plus or minus I. And there are all 4 of these roots. And we were expecting 4, and we got 4. The pluses or minuses give us the remaining 2. My first instinct here is grouping, but it doesn't look like it's going to work with grouping. So my next thought is I want to test rational roots, and I'm just going to test them until I find one. So 1, 3, negative 9, 5. One possibility would be 5. Let's see, 1, 5, 8, 40, 31. I already know this is a no. I don't have to do the math to know that that's a no. Another option would be, let's see, negative 5 maybe. So we get 1, negative 5, negative 2, positive 10, positive 1, negative 5, 0. So yes, we just found one root there, and then this gives us the following quadratic: x squared minus 2x plus 1. Is that factorable? I think so. I think just write it out to be sure. X minus 1 and x minus 1, those add up to be negative 2 and multiply to be positive 1. Yep. And so then we get x equals 1 mult 2. So those are roots 2 and 3. I think we got, so 5 and 1 multi 2. Let's see if we got that right. 5 and 1 multi 2. Good. Let's see, we got another quadratic form. This one's kind of interesting. We got to pull out the greatest common factor, which is an x squared, leaving behind an x squared plus 6x plus 5. This factors into x plus 5 and x plus 1. We got that x squared. This gives us a 0 multi 2, a negative 5, and a negative 1. All right. Write a polynomial function of least degree with integral coefficients in standard form with no fractions. That is the given zeros. I did number 15 in the slideshow, so you can look there for number 15. Let's do 16. So if negative I is a root, I know I must also be a root. That is the conjugate root theorem. All right. Now I can write out my roots, x plus 1, x plus I, and x minus I. Let's FOIL out the conjugates first, because we know we'll get some good canceling. We'll say plus ix, or technically if I'm foiling it would be minus ix plus ix. Those are going to cancel. Minus I squared, that becomes a negative 1. At x plus 1, that whole thing, x plus 1, x squared, these here cancel. That I is equal to a negative 1, so this becomes a plus 1. And we FOIL one more time, and I'm going to do it so that I get it in standard form right away. First, inside, outside, last. There we go. I'll do one more. We'll do this one with fractions. For 18, don't forget to do a 1 plus I, but I won't solve that one. So I need to have the fraction 4/3 as a root, and I need to have it twice. So I got to put the factor in there twice, and I need to have x minus 3/2 as a factor. All right, what I can do here to make my life a whole lot easier, multiply this whole factor by 3, this whole factor by 3, this whole factor by 2. That doesn't change where the roots are, but now I'm not dealing with fractions. Two x minus 3. Now I've just got a lot of distributing to do, but without the fractions, my life is a lot easier. 9x squared minus 12x minus 12x plus 16. 2x minus 3. That's become 9x squared minus 24x plus 16. 2x minus 3. Keep going. To make sure I do this distribution right, I might draw some arrows of what I plan to distribute. So that gives me a 18x to the third minus 27x squared. I'll do, my next arrows will go from here to here, here to here, giving me a negative 48x squared and a positive 72x. And my last distribution will go there and there, giving me a 32x and a negative 48. Combine my like terms, and I get 18x to the third. Don't want to make any mistakes here. Minus 75 x squared plus 104x minus 48. Check and see if any of those have common factors. I don't think they do. Let's just see if I got that right. Oops. 18, negative 75. Yep, that's right. All right, so we'll end the video there. Hopefully this has been helpful. I will see you in class.